Hi everybody, today we are going to look at some important polynomial theorems. Is it important to memorize these theorems? No, but it is important to understand what they're about. So the first thing we're going to do is we're going to use something we know to lead into a theorem. So it says use synthetic division to find a certain f of x. So for example, if we are given this polynomial right here and asked to find f of 2, normally we would just plug 2 in, right? But it's asking us to use synthetic division to find that. And so what we're going to do is we're going to put our 2 in our little box, and we're going to use synthetic division. I'm going to change the thickness. All right, so we're going to go ahead and we're going to put the coefficients, right? So we'll put 1 and 4 and -9 and -36, and we'll drop down the 1. We'll start multiplying. Right, 4 plus 2 is 6, and we'll multiply again, and then we'll add again, and we'll multiply again, and we'll add again, and we get -30. So you're like, okay, what did we just do? Well, let's stop and see what we just did, because we're going to compare what we just got, that -30, to what we would get if we actually did plug in 2 into this polynomial over here. So let's go ahead and find what is f of 2. Let's plug in the 2 for every single time we see the x, right? And let's see what we get. So we're going to get 2 cubed is 8, 2 squared is 4, 4 times 4 is 16, -9 times 2 is -18, and then -36. Because I don't have a calculator, I'm going to have to do it by grouping. Let's see. 16 minus 18 is -2. -2 minus 36 is -38. So 8 minus 38 is -30. We got the same thing. All right, so that's pretty cool. We just figured out another way to find the value of a function at a certain x. Now, I'm not going to lie, I think this way was faster than that way, certainly less writing. And so why are we doing this? Well, what we just did shows the remainder theorem, right? So the remainder theorem says that whatever remainder we get when we do synthetic division, or regular division too, regular polynomial division, whatever remainder we get is actually the same thing as the value of the function when we plug our number into the function itself. Pretty cool. So do you need to memorize it? No, but you just need to remember, oh, this remainder is the same as if I plugged the number in. And so that's more of an official way of saying the remainder theorem. And it's saying divided by x minus a. Remember with synthetic division, whatever number we put in here, it's just a shortcut, right? We're not really dividing by 2. We're dividing by x minus 2. And you learned that last class. All right, so the cool thing is that, hey, when our remainder is equal to 0, then we know that we have a factor. So for instance, if we go back here, our remainder wasn't 0, which tells us, yeah, 2 didn't go in evenly, so that means x minus 2 is not a factor, right? But if we got a remainder of 0, we would say, 2 goes in evenly, which means x minus 2 is a factor. So when we look at the factor theorem, it's just a very specific way, an extension of the remainder theorem, all right? And we're going to use the factor theorem today. And so there we go. How to use the factor theorem. It says if x minus 2 is a factor of this function, then use it to find the remaining factors. When you found the remaining factors, write the complete factorization of f of x. This is a couple different parts, right? So stay with us. I'm going to pick pink for this. You know, we just never use how about magenta, kind of. That looks so good. And let's go ahead and make it a little bit easier to read. Here we go. So the first thing I'm going to do is, it told me x minus 2 is a factor. So I'm going to use that and say, hey, that means if I plug 2 in and use synthetic division, I'll get a 0 for the remainder, and that's going to be a big deal, and I'll show you why in just a second. So remember, to know what to put into this box, you set whatever your factor is equal to 0, and you solve, and that number is what you put into your box. All right, so let's go ahead and write out the coefficients. We've got 1, -1, -14, and 24. Let's go ahead and do synthetic division. We'll drop it, we'll multiply, we'll add, we'll multiply, we'll add, we'll multiply, and wow, a 0. That's not a surprise because they told us it was going to be a factor, and we know the factor theorem says if it's a factor, you're going to end up with a remainder of 0. But the cool thing is what we have left. And I know you did this last class. This, and this are just the coefficients for a function, right? I always start right next to the remainder. I start here with the negative 12 because I know this is always my constant. That's my negative 12. This coefficient is whatever number is in front of the x. So I have a 1x. I'm just going to write x. And this is the coefficient in front of your x squared. So I'm going to write x squared. So, let's just write what we just figured out. We said, hey, when we looked at this polynomial and we divided it by x minus 2, it went in evenly, and what was left was this, the x squared plus x minus 12. Now, we could continue to use synthetic division to factor this completely, but I'm like, hey, that's a quadratic trinomial. I can go ahead and just factor that out, right? So we already know x minus 2 is a factor. They gave that to us. And then we're going to break down this quadratic that we got from using synthetic division. And we're going to say two numbers that multiply to equal negative 12 that add to equal positive 1. That's going to give me a plus 4 and a minus 3. I'm done. So find the remaining factors, then right, there we go. So when you see this in WebAssign, I'm pretty sure it's WebAssign, not Delta Math, but when you see this, this is how you're going to answer it. This is considered the complete factorization of this function. Some students forget when they give us a factor, we have to include that in the complete factorization. So just a look over, when they give us a factor, we're going to use synthetic division, and we should, if we do it right, we'll get a remainder of 0. Then we're going to look at the coefficients of what's left, drop those down into the coefficient part of a function. Now, once again, if there were 4 numbers after synthetic division, I'd have a cubic function, right? I would have had a coefficient for x cubed, but I don't. There's just 3. And then what you're left, if you're left with a quadratic that factors easily, factor it, and voila, you are done. All right. Now, not every polynomial is going to be as beautiful as that. Oh, they're all beautiful, but it's not going to be as beautifully easy as that, right? So we've got another theorem. It's called the rational root theorem. Once again, you just have to know what this says. You don't necessarily have to memorize it. You do have to know what your P and what your Q is. Remember that old-fashioned saying, mind your P's and Q's? Well, I don't know if they were talking about this, but yes. Let's mind our P's and Q's. All right, so what in the heck are P's and Q's? P stands for the factors of the constant. So like for this example, for number 1, or well, let's just look at the example that's right over here. For this example, P would be, we're looking at 6 to find our P. So 6 would be, or I'm sorry, P would be all the factors of 6. Well, I know, you're probably really saying, well, 1, 2, 3, and 6. Why are we looking at the negatives? We have to look at the negatives. They're technically factors. We don't really, when we make factor trees, we don't consider the negatives back then because we didn't know that we needed them, but technically they are factors, right? Negative 1 times negative 6, well, that's 6. So negative 1 and negative 6 should be considered factors in this case. So we go ahead, these are all the P's. And then Q are all of the factors of the leading coefficient. The leading coefficient's 1. Thank goodness. We love it when we have a leading coefficient of 1. And the only factors of 1 are going to be plus or minus 1. So what are we doing even here? Why are we talking about P's and Q's? Well, we are looking for possible rational roots. All right? So rational, we got to remember, what in the heck are rationals, right? Well, we've got real numbers, or any number that finds a place on the number line. All the numbers we always work with are real numbers. Rational numbers are any number that can be written in fractional form. Okay, they're rational numbers. And so let's say, 1 over 3, that's a rational number. Yet when you make it into a decimal, right, 0.33333 repeating, but as long as you can take a number and make it into a fraction, it's rational numbers. All right, so let's see. So we're looking at some possible rational zeros. And so what we're going to do with this first one is we're looking at 6. So it looks like we've done that before. Let me go ahead and redo. Let's see. All right, let's change. All right, go back to purple. I seem to favor that. So once again, our P would be, all our P's would be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And then our Q, same thing. So it looks like we're looking at the same problem. Why am I doing the same problem? Oh, because it is the same problem. All right. So I don't need to redo this. We already did it. So when you put the P's on the top and the Q's on the bottom, then you come up with how many different numbers can you get from doing all these divisions. Well, the first thing I'm going to look at is plus or minus 1 divided by plus or minus 1, which gives me plus or minus 1. Same thing, plus or minus 2 divided by plus or minus 1 gives me plus or minus 2. Plus or minus 3 divided by plus or minus 1 gives me the plus or minus 3. Plus or minus 6, you get it, right? It gets to be a little bit more tricky, like with this second example, where we'll have more than just one thing in the denominator. So here we go. Let's do this one. P is going to give me what? Plus or minus 1, plus or minus 3. I like that. Very simple. Q is going to give me plus or minus 1, plus or minus 2. And so P over Q, I could have plus or minus 1 or plus or minus 3. Okay, so here's the deal. If I'm just focusing on the 1, I can say plus or minus 1 over plus or minus 1. All right, that's going to give me plus or minus 1. Plus or minus 3 over plus or minus 1. That's going to give me plus or minus 3. Now we have to see, well, wonder if we use the plus or minus 3. So plus or minus 1 over plus or minus 3, it's going to be plus or minus 1 over 3. And then plus or minus 3 over plus or minus 3, that's still going to give me the plus or minus 1. So here's the deal. We can't always tell when we're looking at a polynomial what the zeros are. So the rational root theorem gives us a place to start. So if we were going to be hunting for zeros for this whole polynomial, we have a place to start. We could see if plus or minus 1 would work, or plus or minus 3, or plus or minus 1/3. One of those would work, if it has a real zero, right? Sometimes these polynomials, they don't have real zeros, and we'll get into that later. All right, so rational root theorem. Just know what your P is and your Q. So here we go. When you see find all the possible, let's use orange. All right, so when you see use all or find all the possible rational zeros, that's a hint. Find your P's and Q's, right? That's going to give you your possible rational zeros. So here we go. My P, once again, we're on the same thing, plus or minus 1, plus or minus 3, and the Q, thank goodness, is just plus or minus 1, right? All right, so when we put P over Q in all the different ways, we could do positive 1 over 1, which give me 1, negative 1 over 1, which give me negative 1, so plus or minus 1. Or same thing, 3 over 1 would give me a positive 3, negative 3 over 1 would give me a negative 3, so we have plus or minus 3. We're hoping that either a 1, negative 1, 3, or a negative 3 gives us, is actually an x-intercept, is a 0. So let's find out. Now, we could go down the road and do 3 or negative 3, but I always like to cheat a little bit. And I mean, it's not really cheating, but I like to try my 1 first to see if it works. So I'm going to try it real quick to see if I plug in a 1 here, I'd have 1 cubed minus 3, 1 squared minus 1 plus 3. And I'm like, oh, it does work. 1 cubed is 1. That 1 cancels out with the negative 1. 1 squared times 3 is negative 3, because that negative there cancels out. That is a 0. Now, I'm still going to use synthetic division, though, but it just gave me a little jump start. It's a little cheat to your trial and error. I know 1 is going to be a 0. So what I'm going to do then is I'm going to use it in synthetic division to see what I have left after I divide by it. So we're going to bring down our coefficients. We're going to use synthetic division. All right, we got 1 times 1 is 1. That's negative 2. That's negative 2. That's negative 3. And of course, we knew it is a 0, so we have a 0 there. But look at the gift it gives us. Once we know one of our zeros is 1, so let's not lose that. X equals 1 is one of our zeros. Let's use this, what we have left, to find our remaining zeros. So we're going to go ahead and rewrite it. We know that negative 3 is a negative 3, that negative 2 is a coefficient in front of the x, and that 1 is a coefficient in front of the x squared. Can we factor this? You betcha. Let's go ahead and factor it. Once again, now it's a quadratic that's left because we just divided by x minus 1, or we use synthetic division with 1. And so we're going to go ahead and set this equal to 0 to find our remaining zeros. We're going to factor. I'm going to use what? Negative 3 and positive 1. So we know that our remaining zeros will be 3 and negative 1. So our zeros are x equals 1, negative 1, and 3. Could you write it as plus or minus 1, comma 3? Sure you can. I'm not sure which way WebAssign will want you to do it. But there we go. We found all the actual zeros. Yay! So step 1, we used our P's and Q's to give us an idea of what a zero could be. We did a little cheat and just plugged in 1 into the polynomial. You don't have to do that. You could always just do still a cheat. It's just to start with a 1 with synthetic division. But you know you hit gold when you get 0 for your remainder, because then whatever you have left will help you to find the remaining zeros. Okay, other ways to find the real zeros of a function, go to Desmos, right? Because this is a mess right here. This would take a long, long, long time. We could go to Desmos and we could see that actually the zeros look quite lovely, right? There's a 0 here at x equals 2, there's a 0 here at x equals 5, and there's a 0 at negative 1/3. So that didn't look that bad. All right, let's see what else we're doing today. All right, and remember, we can use factoring to find real zeros. So this obsession on the zeros of a function, it's very real because it helps us to graph, but also there's a lot of interesting things going on when the function's equal to 0. It's very meaningful in some real life applications. Unfortunately, we focus most in this class on the skills so that we can do the calculus and see some more applications there. All right, let's go ahead. This is factoring by grouping. I think we probably need another example of this where we look at the first 2 terms and the second 2 terms. We're going to do some separate pulling out the GCF. So we look at these first 2 terms and we say my GCF is x squared. That pulls out an x. I'm sorry, we pull out an x squared, what's left? An x plus 4. And here our GCF, whenever we have a minus, we want to factor that out. That's yucky. We want to go ahead and factor out that negative 9. What do we have left? That's right, x plus 4, right? If I distribute the negative 9 back, I would get negative 9 times x, which is negative 9x. Negative 9 times 4 is negative 36. So yes, and we know we're on the right track when we have the same number or the same binomial there and there. So what's in common with this term and this term? You betcha, that x plus 4. When we factor out the x plus 4 from this term, it's like we are dividing by x plus 4. And what's left is x squared. When we're taking this term and factoring out an x plus 4, we divide by x plus 4. What's left? The negative 9. All right, so then we've got, let's just keep going. We've got x plus 4 equals 0 and x squared minus 9 equals 0. So we've got x equals negative 4. And in this case, you could either factor the difference of 2 squares or just go ahead and use the square root method, right? We'll have x equals plus or minus 3, right? Because if we do plus or minus square root of 9, right, we'll get plus or minus 3. So what are our zeros? Our zeros are plus or minus 3 and negative 4. All right, so we are building a good case to get to the end goal, which is to have a greater understanding of polynomials, especially their polynomial graphs. All right, thanks for joining me.